Hello and welcome to Cashmatics. This is part 2 of my series of videos on using the reverse chain rule. And just as before, we're going to consider some derivatives to begin with. And once we've done that, we'll look to see how we can apply this reverse chain rule in what I consider slightly trickier problems than the ones in the last video. So, as always, grab yourself some paper and a pen and we'll get started. So we've got 3 examples here which we're going to differentiate, and hopefully from these we're going to be able to work out what the rule is for using the reverse chain rule. So let's just differentiate these. So dy by dx, so this is something to the power 5, so remember, multiplied by the power, take 1 off the power and multiply by the derivative of this bit here, which is 6x. And let's just tidy that up. So that's 30x, 3x squared plus 1 to the power 4. Okay, this one here, before I differentiate it, I'm just going to rewrite this as sine x cubed to help you to see what's going on. So dy by dx, remember something cubed becomes 3 something squared, multiplied by the derivative of this, which is cos x. And I'm going to write that as 3 cos x sine x squared. So I'm going to write it like this, so hopefully you'll be able to see what's going on when I explain it all. This one here, so again I'm going to write that as tan x to the power 4. So dy by dx would equal 4 tan x to the power 3 multiplied by sec squared x. I'm going to rewrite that as 4 sec squared x tan x cubed. Okay, so let's just try and make some observations here. Okay, so the bit in the bracket in all of these examples, okay, the bit in the bracket which I've got here, this bit here is f of x. So it's f of x to some power, okay, in this case the power 4, and this is some multiple of the derivative of f of x. So 3x squared plus 1 becomes 6x, and this is a multiple of that. Okay, again here we've got f of x squared, okay, and this is k times f dash x, because if f of x is sine x, the derivative is cos x, and this is 3 cos x. So again, it's a multiple of that derivative, and the same goes here. This bit here is f of x to the power 3, and this is k times by f dash x. So integration is the reverse of differentiation, which means if I want to go from here back to here, let's just look at what's happening to the power. Okay, so this is the power 4, so that's to the power 5. This one here is to the power 2. This sine x is to the power 2. So the function itself I'm talking about is to the power 2, and the original one is the same function but to the power 3. Here, this function here is to the power 3, but the original was the same function to the power 4. So what we can conclude from that is, if I've got an integral which is in the form f of x, or k times f dash x multiplied by f of x to some power, okay, so all of these are k f dash x multiplied by f of x to the power, so they've all got the same form. So if I was to integrate that, what I need to do is consider the derivative of this function here. It's going to be something to do with this. Okay, so I would add 1 to the power of this function. Okay, I would divide by that because I don't actually want that power. I divide through by that power and then tweak it. Okay. Now, put that in your notebooks. I think that'll be useful to you, but it's not really going to make an enormous amount of sense until I go through some examples. So I'll go through some fairly straightforward examples and then some trickier examples. So hopefully by the end you'll be able to see how this rule works. So let's have a look at this example here. Now, the key to getting these right is to understand which bit is the function and which bit is the derivative. So in this case here, it's this bit that's the function, okay, the 2x cubed plus 1. And the derivative of 2x cubed is 6x squared, okay. Now, when we're doing this, we need to make sure we consider the following, which is this bit here on the right. So my starting point is always by writing this bit here, okay. So I'm going to write 2x cubed plus 1 to the power 8 over 8, okay. That's going to be my starting point. Now in this case it actually works, okay. If this is the exact derivative of this, okay, so the exact derivative of 2x cubed plus 1, then this will work, because if I was to differentiate this, I would get 8 times by 2x cubed plus 1 to the power 7 multiplied by 2x cubed, well, the derivative of 2x cubed, which would be 6x squared, and I've also already got the 8 underneath, so that 8 will cancel that 8 out, and that's the reason for dividing by that 8, and I've got the exact thing I'm looking for, okay. So that's if this bit here is the exact derivative of this, so not a multiple of it, but the exact derivative of it, then it's all you need to do is apply this rule here and you get your answer. Now in this example here, at first glance it doesn't look like the one we had before. Okay, we've actually got a division here. So your first instinct might be to see if the top is the derivative of the bottom. Okay, and the top is not actually the derivative of the bottom. Remember, that rule only works if the top is the exact derivative of the bottom. That power changes things here, because the power would make it 3 brackets x squared plus 4 to the power 2 multiplied by 2x. So the top is nowhere near the derivative of the bottom. The key to understanding this one here is to rewrite it. So if I rewrite it as x brackets x squared plus 4 to the power minus 3 dx, now what we've got is this bit is your f of x, and this bit is a little bit like the derivative of f of x. Okay, the derivative would be 2x, and that's just an x, which means there's a factor of 2 that we need to consider. So the first thing we do is just add 1 to the power here and divide by the new power. Okay, so I'd say x squared plus 4 to the power minus 2 divided by minus 2, add c, and then think what it is that's missing from here, which will get me the correct integral. Okay, or I could differentiate this and see if I get back here. So let's just try that. We can try it both. We can try it both ways around, but I prefer doing the derivative of this. So the derivative of this would be minus 2 x squared plus 4 to the power minus 3 multiplied by 2x, and what we've got that's missing. Okay, well, let's just put the minus 2 on the bottom. So that would cancel that out, which is fine. So the minus 2 would keep that. What I'm missing here, or what I need to also get rid of, is this 2. This 2 is extra. So if you look at it, I haven't got the 2 here. So the 2 is extra, so I need to multiply this by 2 again. So my final answer is minus x squared plus 4 to the power minus 2 divided by minus 4. Sorry, divided by 4, sorry. I've already taken care of the minus sign, so let's just get rid of that. Okay, I've already took care of it here. Plus c. So I hope that's made sense. What you need to do is tweak the answer to get the right integral. Okay, next example. In this one here, we need to work out which bit is the function and which bit is the derivative. Okay, so tan differentiates to become sec squared. So think of this as tan x squared. So this is your f of x, and this bit here is your f dash x. Okay, so what we've got is we've got the exact derivative. Okay, so this is the exact derivative of f of x. So we can apply the function exactly as it is here. So all I need to do is tan cubed x over 3 add c. Okay, it's as simple as that. Right, next example. So this one's a little bit clearer, I think. Okay, so this bit here is your f of x, this bit here, it's not quite f dash x, because f dash x would have been 2x plus 2, and this is just x. This is just x plus 1. So we know we need to get rid of a factor of 2. Okay, so it should be quite straightforward. So what we need to do here is increase the power, x squared plus 2x plus 3 to the power 5, divide by that new power. Okay, but we also need to divide by that factor of 2, which we would generate from here, which we need to get rid of. Okay, so that would be my final answer, and let's just tidy that up. X squared plus 2x plus 3 to the power 5 over 10, add c. Now the next two examples are slightly trickier because we've got an e function or an exponential function, and what we need to consider for these is that this bit here is your f of x, and this here is your f dash x. So it's not as straightforward as the other ones, but we still got the derivative times its function. So we can still use the reverse chain rule, but we're not using it in the way we've been using in the past few examples. So what I would do is I would consider what the derivative of this bit is. So e to the x squared. Okay, and that would give me e to the x squared multiplied by 2x. And that just happens to be that exact integral there. Okay, so that means if you differentiate this to get this, that means if I integrate this, I'll get this. So the answer to this is e to the x squared plus c. And similar to the last example, what we've got here, this bit here is your f of x, this bit here is your f dash x. So just as before, all I need to do is consider, let's just get rid of this. All I need to consider is the derivative of this. So d by dx of e to the sine x would be e to the sine x multiplied by cos x. Okay, and that's exactly what I've got here. So if the derivative of this is this, that means when I integrate this, I'll get this. All right, so that means the answer is e to the sine x plus c. And if you did have a number in front of here, so if you had a 2 in front of here instead, all I would need to do is put a 2 in front of there. Okay, if I had something over 3 there, I just need to make sure I put something over 3 there. So I hope that's helped. And you need to make sure you distinguish between the type of chain rule questions that I put in the first video compared to these ones here. And I'll just summarize both of them if I can. So what you need to think about is if you have the function over, so the derivative over the function, then if it's exactly that, you'll get ln f of x plus c. And if it's not exactly that, if it's say if it's k times if it's something times the derivative of the bottom, then you just need to tweak the final answer to cancel things out or to introduce things. And if your integral is in this form, sorry, not plus c, dx, it would be f of x to the power n plus 1 over n plus 1 add c. And if this isn't the exact derivative of this, then you might just need to tweak it by sticking in some factors at the start. So I hope that's helped. And yeah, next time we'll be looking at integration using substitution, which is a really powerful tool which can be used to simplify some really nasty looking integrals into something which is very manageable. So hopefully I'll see you next time. Goodbye for now.